Alright, let's look at some Boolean operations in Matlab. So suppose I want to do an AND operation. 1 and 1. And here it returns a 1. So when I'm Boolean operation here, and where the inputs are 1, which represents a logical true, and 1, which represents a logical true. Two logical trues ANDed together return a logical true. If I use a 0 here, I get a 0 back. 0 is a logical false, so I have a true ANDed with a logical false, and I get a 0. Now notice that I'm using two AND signs here. I could do the same thing with one AND sign, and I would get the same result in this case. The two AND signs are going to only evaluate, they're going to stop the evaluation. For example, if the first input to the AND was a logical false, it would stop evaluating. It wouldn't look at the rest of it. So if I'm dealing with scalars, I can use the double ampersand. But suppose I wanted to, for example, if I have a vector A and a vector B, if I want to take the logical AND of those two vectors, I would have to do A with a single AND sign B. And you see here it returns a vector which has the results of A and B element-wise for A to B. So 1 and 1 ANDed together gives us a 1. 0 and 1 is 0. 1 and 0 is 0. 0 and 0 is 0. If I tried this, I get an error. I can only use the single AND sign when I'm dealing with logical scalar values. Also, if I'm going to use my logical operator, for example, in an if statement to evaluate whether something is true or not, Matlab prefers, in that case, that I use the double AND sign. We can do this vector operation for the OR. Okay, so A or B. Here I get 1, 1, 1, 0, 1 returns a 1, 1, 0 returns a 1, and 0, 0 returns a 0. I can also do an exclusive OR. Exclusive OR in Matlab is done like this. Okay, and we can see here, if we look back at A and B, the first two elements, 1 exclusive OR with 1 gives me a 0. 0 exclusive OR with 1 gives me a 1. 1 exclusive OR with 0, a 1, and then 0, 0 gives me a 0. So suppose I had a script, and here I'm taking two scalars, A and B. Initially they're going to be 1. And I'm going to loop through this operation 10 times. And inside the loop I'm going to say if A and B, and that means if A and B is true, I'll display true. Then I'm going to let B equal 0. Else, display false and make B 1. So if I run this script, we see the output here, true, false, etc. What's happening here is initially A and B are 1. So I come into the loop. My if statement evaluates true here because A, which is a 1, and B ANDed together give me a 1, which is true. So I display true, but then it sets B equal to 0, loops through. So the next time through the loop, A and B evaluates false. So we display false, then it sets B equal to 1. If I made A 0 at the beginning of this script and ran it, it would never evaluate true. Okay, because whether B is 1 or B is 0, A being 0 makes it so that this always evaluates false. I can do an OR here. Now since A is 0 and B is 1, this OR will evaluate true. But then it's going to set B to 0, so then both my variables are 0. So the next time through the loop, it doesn't evaluate true, it evaluates false. And we see we get true, false, true, false. and so on as it scrolls through. Okay, so the main points here is Matlab allows us Boolean operations. The main ones that we'll use are AND, or exclusive OR. And one of the main places that we're going to use these Boolean operations is to evaluate whether an if statement is going to evaluate true or false. Keep in mind, suppose I wanted to determine if A was equal to B, that would be a double equal sign. And if I run that code, initially A is equal to B, so it displays true. Then it sets B equal to 0. And the second time through, it's not true, so I get the false. Then it sets B equal to 1, and you can see that it iterates through again. Okay. Something else I want to look at is multiplication in Matlab. I have two vectors here, A and B, and I want to look at the different ways that we can multiply these together. Now, if I do A times B, I'm going to get an error because A times B is not a valid operation. However, A times B transpose is valid, okay, and in this case I would get the scalar 1. Also, A transpose times B is a valid multiplication, and I get a vector, a 4 by 4, or a 4 by 4 matrix if I multiply A transpose times B. So you can see that here Matlab is simply following the normal multiplication rules for vectors. But suppose I wanted to, let's change these around. Suppose I have A that looks like that, and B that looks like that. Suppose I wanted to multiply these together element-wise. For example, for some reason I need to multiply the first element in A times the first element in B, and the second times the second, and so on. In order to do that, I use the dot times operation, and this gives me element-wise operation. So you can see what I got here. First of all, I was able to do A times B. 3 times 2, 6. 6 times 4, 24. 9 times 6, 54. And 8 times 12, 96. So it went element by element. Similarly, I can raise things to a power. So I could do, if I do A to the B power, I'm going to get an error. However, that is a legal operation. It gave me 2 to the 3rd, 4 to the 6th, 6 to the 9th, and 8 to the 12th. You can see that this first one is actually equal to 8, but there wasn't enough significant digits for you to see it. Same with the second one and the third one. I overwrote answer when I got that 8 there. But if we do this again, we can see that this one is actually equal to 4096. Now, if I have a matrix, I can raise the matrix to a power only if it's square. What did this do? Well, it took A times A times A. And that's only legal if A is a square matrix. If it's not, I can't multiply A times A. So Matlab only allows this, as you would expect, for square matrices. Okay, another useful topic is finding the roots of polynomials. We can use Matlab to find the roots. Many times it's useful to be able to find the points where a polynomial evaluates to 0. So let's create P, and let's make P, for example, a vector that looks like this. Now, if I use the command roots P, what Matlab did here is it evaluated the roots of the polynomial that has the elements of P as its coefficients. Okay, so here P has 1, 2, 3, 4, 5 elements in it. So this would be x to the 4th minus 12x cubed plus 0x squared plus 25x plus 116. And Matlab evaluated the points where the values of x, for example, where that polynomial is 0. And we see that 2 of them are real, and then the other 2 are complex conjugates. So there's 4th order polynomial, 4 roots. In this case happens to be 2 real, 2 complex. We could also, now all I've done here is created a variable b that allows me, that has the values that are the roots in it, and I can use the command poly. Now what it's done is it's figured out the polynomial that has the roots that I specified. Okay, so these operations go both ways. We can evaluate the roots of the polynomial, or given the roots, Matlab will find the polynomial for us. We can do polynomial multiplication here. So suppose I have for example, I have these two vectors a and b, and I want them, for example, a is going to represent x cubed plus 2x squared plus 3x plus 4, and then x cubed plus 4x squared plus 9x plus 16. And so I want these to represent polynomials, and I want to multiply the two polynomials together. The command that does that is conv. Okay, now you can see that I get a 6th order polynomial. Okay, x to the 6th plus 6x to the 5th plus 20x to the 4th plus 50x cubed plus 75x squared plus 84x plus 64. Okay, and then suppose I wanted to find the roots to that polynomial. I can do that, and we see we have 2 real roots and then 2 sets of complex conjugate roots. If I wanted to add the 2 polynomials together, I could do that as well. And so here, if I add a and b as polynomials, I get 2x squared, or 2x cubed plus 6x squared plus 12x plus 20, which is fine. Keep in mind that if the polynomials were of different orders, then I would have to pad them with zeros. So, for example, suppose I will change a to be x squared plus 2x plus 3, and we will make b equal to 3x cubed plus 4x squared plus 3x plus 9. Okay, so now if I just do a plus b, I'm I'm going to get an error because the dimensions don't agree. So what I have to do is go back and pad A with a 0, and now I can do A plus B and get the result that I'm looking for here. Suppose I wanted to take the derivative of a polynomial. If I want to do that, I use the command poly, der, and suppose I want to find the derivative of this polynomial. Poly derivative will return that derivative. So that's a useful, something useful to do. And let's look at another polynomial here. Another polynomial P. And suppose I want to evaluate this polynomial. Well, I need to use a command called linspace. This creates a linear space. And suppose I want to look at it from -1 out to 3. And now I can evaluate the polynomial over that linear space using the command polyval, the polynomial, and then where I'm going to evaluate it. And then I can plot the result. And here you can see that in the range from -1 to 3, we've evaluated and plotted the values of the polynomial P. Okay, which in this case is x cubed plus 4x squared minus 7x minus 10. Notice that when I plot it, I put what's on my x-axis first, which is this linspace x, and if you want to see what that looks like, you can see that all it is it's created essentially a vector that ranges from -1 and steps up to 3. Suppose I had a ratio of polynomials, which, for example, in a transfer function, I would have something like that. So I can say for example, I have something I'll call n, which is going to be the numerator, polynomial in the numerator, and then I'll call the one that'll be in the denominator d. I have my numerator and my denominator, and in order to deal with this type of a situation where I have a polynomial in the numerator and a polynomial in the denominator, I'll deal with the numerator and the denominator separately. So for example, if this were a transfer function, I can find the zeros of the transfer function, which would be the roots of the numerator, and then I can find the poles of the transfer function, which would be the roots of the denominator. Okay, so you can see here I have zeros at -16.18 and 6.18, and I have poles at 0, -5 plus 8.6i, and -5 minus 8.6i. Earlier we showed an example of a for loop. For loops are good control flow constructions for when we want to evaluate a group of commands a fixed number of times. We want to loop through a fixed number of times. Another common loop is called a while loop. A while loop is good when we want to evaluate something an indefinite number of times. So suppose we'll start with some variables, n equals 1, m equals 2, and we'll create a while loop that says while sum is less than 20. And each time we go through this loop so that we can see some output, we'll display something. We'll just say yet another iteration of the loop. And we will let sum be equal to itself, which will initialize sum at 0 up here. And then we're going to add to it n, and we'll add to it m. And let's see. Okay, so we run this, and we see here 1, 2, 3, 4, 5, 6, 7 iterations of the loop. Okay, so we started at 0, and we added 3 each time we went through the loop. So after the 7th time, we get to a number that's greater than 20, and the loop stops iterating. So that's an example of how you can use a while loop. Now we can also, for example, we can say while, let's say tr. We can do something very similar. Let's say if sum is less than 20, tr will be equal to 1, else tr will be equal to 0. So here we're using tr as a Boolean, and it'll remain true until the sum goes over 20. So this code should really do exactly the same thing as the previous code did, but you can see that we're using a Boolean in our while loop instead of using a less than statement. And if we run it, we need to initialize the value tr. So this is a good opportunity to see what happened here. So we run the code, and it gets to this statement on line 5 here that says while tr, and tr doesn't exist yet. It's not created until we get down here. So we need to initialize it. So let's initialize it as true. And we'll run the code. Okay, and you see we get the same thing. 1, 2, 3, 4, 5, 6, 7 iterations of the loop, basically doing the exact same thing as the previous code that we ran.